Hello guys. The purpose of this video is to demonstrate how to do the calculation for the molar volume of a gas lab report. In the previous video we demonstrated how to do the experiment for molar volume of a gas, and we collected the following data. We collected the massive magnesium sample was 81.3 milligrams or 0.0813 grams. The volume of hydrogen was 82.20 mLs. The temperature of hydrogen gas was 24.1 degrees Celsius. The temperature of water was 25.2 degrees Celsius. The difference in water levels, the column of water was 17.95 centimeters, which is equal to 179.5 millimeters of water. Okay, we did not take the barometric pressure, so to show you how to do the barometric pressure, if you do not have a barometer available in the lab, we can open our browsers and go to weather.com, search for the zip code where the experiment was conducted and hit enter. If you scroll down, okay, it will give you the pressure right here in inches per mercury. So today's pressure, or the pressure right now, it's 30.02 inches of mercury. So we can record this temperature right here under barometric pressure. That's the total pressure. So we will enter and say that this is 30.02 inches of mercury. Now what we should do is convert this to millimeters of mercury, and in order to do that, let's do that right here. Okay, we know that 1 inch will equal exactly 2.54 centimeters, and that will be centimeters of mercury. The inches here will cancel. Now I have my pressure, and my pressure right now is in centimeters of mercury, and I could do another conversion that 1 centimeter of mercury is equal to 10 millimeters of mercury. Centimeters of mercury cancels, and now I could get my calculator and calculate 30.02 times 2.54 times 10. I get a pressure of 762.51 or 0.5 millimeters of mercury. Now that we determined what the barometric pressure is using weather.com, the barometric pressure is 762.5 millimeters of mercury. The first data calculation is number 1, aqueous vapor pressure. If you remember from the video of the experiment, aqueous vapor pressure has to deal with the temperature of water, which here in our data it's 25.2 degrees Celsius. The higher the temperature of water, the higher the vapor pressure. The lower the temperature of water, the lower the vapor pressure of aqueous vapor pressure. So we can go to our handout, or our handout for the experiment, and if we go to page number 2, we have a table for vapor pressure of water. Now our temperature is 25.2 23.2 degrees. So we are between 25 and 30. So our vapor pressure will be much closer to 23.76 millimeters of mercury, simply because we're at 25.2 than at 31.8. But we will calculate it exactly. Okay, so let's start to calculate what the vapor pressure is exactly at 25.2. So if we record what we see in the data table, at 25 degrees Celsius, the vapor pressure is 23.76 millimeters of mercury. At 30 degrees Celsius, the vapor pressure is 31.82 millimeters of mercury. Of course, our water temperature is 25.2 degrees Celsius, so we are much closer to 23.76 than we are to 31.2. So first we're going to determine the difference of pressure per degree, very similar to what we did in question number 3 of the ASA of the advanced study assignment. So here what we will do is we'll subtract 31.82 millimeters of mercury minus 23.76 millimeters of mercury, and then divided by the change in degrees Celsius, which is 30 degrees Celsius minus 25 degrees Celsius. There's also a sample calculation in your handout that will help you with this. Now get your calculator and let's calculate this. So this is 31.82 minus 23.76. So the numerator is 8.06 millimeters of mercury. The denominator is 5 degrees. We could even do it per degree by dividing 8.6 divided by 5. We get a value of 1.612 millimeters of mercury per degree. Okay, so now I know between 25 and 30 the pressure changes at a rate of 1.612 millimeters of mercury per degree. Now I am 0.2 degrees away from 25. So what I will do is I want to measure how much pressure that will change in 0.2 degrees. So I will do 0.2 degrees times 1.612 millimeters of mercury per degree. The degrees cancel, and now I can calculate, and I see that this here will be 0.32 millimeters of mercury. Okay, so I know at 25 degrees Celsius my pressure is 23.76 millimeters of mercury. If I add 0.2 degrees Celsius to it, that will increase the pressure by 0.32 millimeters of mercury, and that will give me a temperature of 25.2 degrees, which is my water temperature. the pressure at that temperature will be 23.76 plus 0.32, which will give me a pressure of 24.08 millimeters of mercury. Line 2 of the calculations says absolute temperature. This refers to the temperature of hydrogen gas, which is collected in line 3 of the data collected from the experiment. The temperature of hydrogen gas in the experiment was 24.1 degrees Celsius. We need to convert this to absolute temperature, in other words, convert it to the Kelvin scale. So in order to do that, we need to add 273.15 to the temperature in degrees Celsius, and that will give us the absolute temperature of hydrogen gas. So let's do that. So let's add 273.15 and get your calculator, calculate it. You will get 297.3 Kelvin. So that means my absolute temperature is 293.7 Kelvin. Next, line 3 of the calculation is asking for mercury equivalent of the difference of water level. The difference of water level is collected in the data points in line number 6. This was the difference, or this was the amount of water that was left in the odometer in the tube. And remember, we measured this from the surface of the water in the beaker to the meniscus of water in the tube, and we've measured it to be 17.95 centimeter. We converted this to millimeters of by multiplying it by 10, and just to show you why this is the case, okay, 17.95 centimeter. There are 10 millimeters in every centimeter, so the centimeters cancel, and this is how we got our 179.5 millimeters. Now this is millimeters of water because the column contained water. Now calculation 3 is asking for equivalent of mercury, or mercury equivalent. And if you remember from the ASA questions, we said that we need to look at the density of water, which is 1.00 grams per ml, and compare it to the density of mercury, which is 13.6 grams per ml. So mercury is 13.6 times heavier than water. So to convert millimeters of water to millimeters of mercury, I need to divide the millimeters of mercury by 13.6. Okay, so here what I will do is I will take 179.5 millimeters of water, divide this by 13.6, and this will convert millimeters of water to millimeters of mercury, and I will obtain 13.20 millimeters of mercury. So here the calculation will simply be 13.20 millimeters of mercury for the partial pressure of dry hydrogen. Now if we remember our setup, our experimental setup, we had the barometric pressure, which is the atmospheric pressure of 762.5 millimeters of mercury, the pressure that's acting on the surface of water in the beaker, is being opposed by 3 different pressures. First, the pressure of hydrogen gas that was collected, this hydrogen gas was also collected over water, so it was wet. It had some water vapor pressure inside that we calculated in line 1 of the vapor of the calculation, the aqueous vapor pressure according to the temperature of water. This aqueous vapor pressure is 24.08 millimeters of mercury. So the pressure of the gas will be the partial pressure of hydrogen gas plus the water vapor. But we also had a column of water that we've measured to be 17.95 centimeter. We then converted it to millimeters of water, 179.5 millimeters of water. Okay, we converted it in line 3 of the calculation to mercury equivalent. So the mercury equivalent of 179.5 millimeters of mercury is 13.20 millimeters of mercury. Okay, so if you remember, this is Dalton's law of partial pressure, which states that the total pressure, the barometric pressure, is equal to all of the partial pressures. The partial pressure of hydrogen gas, the partial pressure of water vapor, plus the partial pressure of the column of water. So let's answer and look for the partial pressure of dry hydrogen. Of course, dry hydrogen means without any water vapor, so we have to subtract the water vapor from it. Let's begin with Dalton's law of partial pressure. Okay, and Dalton's law of partial pressure states that the total pressure is equal to all the partial pressures. So here we have the pressure of hydrogen gas, that's what we're looking for in line number 4 of the calculation, plus the pressure of water vapor. This we solved for in line 1 of the calculation, plus the pressure of the water column in millimeters of mercury, which we solved for in line 3 of the calculation. So the total pressure is right here. This is my barometric pressure. It's 762.5 millimeters of mercury. This is going to equal to the partial pressure of hydrogen gas. That's what I'm looking for. The partial pressure of water vapor. The partial pressure of water vapor is 24.08. That's what I calculated in line number 1 of the calculation. So that's 24. Oops, lost the 2. Let me repeat this. 24.08 millimeters of mercury plus the column of water, and since everything is in millimeters of mercury, I will not use millimeters of water. I will use line 3 of the calculation, the mercury equivalent, which is 13.20 millimeters of mercury. This way all of the units match and I can add and subtract without any problem. So to solve for the partial pressure of hydrogen gas, the pressure of hydrogen gas will equal the total pressure minus the vapor pressure plus the column of water, which is 13.20 milliliters of mercury. I do the calculations on my calculator. I find that the partial pressure of hydrogen gas is 725.2 millimeters of mercury. So I will write here 725.2 millimeters of mercury. Okay, line 5 of the calculation is asking for the volume of dry hydrogen gas. Okay, remember in line 4 we calculated the partial pressure of dry hydrogen, which was 725.2 millimeters of mercury, but this was at experimental condition. This was not at standard temperature and pressure, because the temperature of the gas here was not 0 degrees Celsius, but it was 24.1 degrees Celsius. Also, the pressure of the gas was not 760 millimeters of mercury, but was only 725.2 millimeters of mercury. So we need to calculate, okay, we need to use the combined gas law. And if you remember from the ASA video, the combined gas law is a combination of Charles' law and Boyle's law. Okay, so we could use the combined gas law to solve for line number 5 of the calculation. And let's begin by stating what the combined gas law is. So we have P1 V1 over T1 equals P2 V2 over T2. Now what I will do is I'm going to dedicate number 1 to be experimental condition. I will dedicate number 2 to be STP. So for experimental condition, the pressure of gas, of dry hydrogen gas, because remember that's what we're looking for here to compare dry hydrogen gas at STP. At experimental condition, the partial pressure of dry hydrogen gas was 725.2 millimeters of mercury. So that's 725.2 millimeters of mercury. Okay. V1, the volume of hydrogen gas. The volume of hydrogen gas, you will find this in your data. This was line 2 of the data. The volume of hydrogen is 82.20 mLs. T1, the experimental temperature, hydrogen gas, the temperature of hydrogen was 24.1 degrees Celsius. But if you remember, we calculated the absolute temperature of hydrogen gas in line number 2 of the calculation, which was 297.3 Kelvin. And we're going to use the Kelvin. So here I will just write both temperatures so you know where they came from. But I will use the Kelvin scale, 297.3 Kelvin. Now, let me put a line here. STP conditions. Okay, I'm going to write here STP. So this is experimental. This is standard temperature and pressure. So the standard pressure is 1 atmosphere, which is 760 millimeters of mercury. We are looking, oops, this is not 2, this is not 1, this is 2. Okay. We're looking for the volume, so our V2 here is what we're looking for, and we're going to obtain this in millimeters because here we have it in millimeters. And then standard temperature is 0 degrees Celsius, which is 273.15 Kelvin. Okay, so we do have everything except for V2. We don't have V2, so we could rearrange the combined gas law to solve for V2, and this will give us V2 will equal P1 times V1 times T2 over P2 over T1. And now we could just plug in our numbers. Our P1 is 725.2 millimeters of mercury times V1, which is 82.20 mLs, times T2, which is 273.15 Kelvin. We're going to divide this by P2. P2 is standard pressure, 760 millimeters of mercury, times T1, which is the temperature of hydrogen gas, 297.3 Kelvin. Okay. V2, if you notice, millimeters of mercury cancels, Kelvin cancels. We will obtain the volume at STP in millimeters, and if we do the math, we find that it's 72.06 millimeters. Okay, so the volume at STP of dry hydrogen gas will be 72.06 ml. Makes sense because we will have a much lower volume of gas at a lower temperature. So at 0 degrees Celsius, the volume will be 72, compared to at 24 degrees Celsius, the volume will be 82. Line 6 of the calculation is asking for moles of hydrogen. Now, if you guys remember from the experiment video, we said that the limiting reagent for this experiment is magnesium. Hydrochloric acid was added in excess, so magnesium here, this amount of grams, limits the reaction. So let's start by writing what the reaction is first. Okay, so we reacted our limiting reagent, which is magnesium ribbon, in excess hydrochloric acid. This was a redox reaction and a single displacement reaction. Magnesium replaced hydrogen and it became magnesium chloride, aqueous, and the protons from hydrogen were reduced to hydrogen gas. And to make this a balanced equation, we'd add a coefficient 2 in front of HCl. So HCl is our excess reagent, magnesium is our limiting reagent. Magnesium limits the reaction. Okay, and from the balanced equation, every mole of magnesium produces a mole of hydrogen gas, which means if we know exactly how many moles of magnesium the reaction began with, then we know exactly how many moles of hydrogen were produced in the reaction. Now we could obtain the moles of magnesium from the mass of magnesium. Okay, now we are missing the molar mass of magnesium, so we need to go to our periodic table, and if we look under magnesium, we see that the molar mass of magnesium is 24.305. Okay, so we will need to convert 0.0813 grams of magnesium to moles of magnesium. Every mole of magnesium weighs 24.305 grams of magnesium. Okay. This cancels out the moles of magnesium, and according to the mole ratio, every mole of magnesium produces 1 mole of hydrogen. It's a 1-to-1 mole ratio. Okay, this cancels. Okay, and now I have moles of hydrogen. We get our calculator, 0.0813 divide by 24.305. We obtain, we have 0.00334 moles of hydrogen. So we began with 0.0034 moles of magnesium, okay, which produced 0.00334 moles of hydrogen. So the moles of hydrogen is simply 0.00334 moles. So I took the data away because the rest of the report does not need the data. We could just complete it from all of the calculation section. Number 7 asks for the molar volume at STP. Now be careful with both molar volume and STP. First, let's define what molar volume is. Molar volume of a gas is the volume or space occupied by 1 mole of that gas. Okay, so that means the definition of molar volume, okay, or the units for molar volume are liters per mole. Remember, in the ASA we said it's really opposite of molarity. Molarity is moles per liter. Molar volume of a gas is liter per mole. Now, we need to know the volume, the molar volume of gas at STP. Well, in number 5 of the calculation, we calculated the volume of dry hydrogen at STP, and that is 72.06 ml. In number 6, we calculated the moles of hydrogen, which is 0.00337. So I can calculate, first I need to convert milliliters to liters. So I will convert 1 liter is 1,000 milliliters, and this will give me 0.07206 liters. So I have the liters of gas, it's 0.07206 liters. I'm going to divide this by the number of moles, which is 0.00334 moles. Okay, I will get my calculator and I will calculate. So I have 0.07206 liters divided by 0.00334, and here I obtain a molar volume of 21.57. Now I'm really limited to 4 sig figs, but I'm gonna cheat and I'm gonna add a 5th sig fig so I can compare it to the molar volume of ideal gas. So this will be a 5 liters per mole. So my molar volume for this experiment is 21.575 liters per mole. Okay, the last part of the calculation are asking for the molar volume at STP, so the average molar volume at STP. Unfortunately, we can't do average molar volume with our data because we only did 1 trial, so we don't have a second trial to take an average. But you guys on your report and in your experiment, you would have 2 trials, and you have the molar volume at STP for 2 trials, and you would just get their average. Okay, so you would add both of them up and divide by 2 because there are 2 trials. That would give you the average molar volume at STP. And then we would calculate their average deviation. Now we'll learn about average deviation when we meet together. Okay, so you will know how to calculate the average deviation, but for two trials it's very easy. You just subtract one of the trials minus the average, because the average deviation will always be in the center of two trials. If you have more than two trials, then you would have to actually sit down and calculate it. But we here, because we only have two trials, so we could, after we obtain the average, just subtract one of the trials minus the average. That will give you the average deviation. Last one is the percent deviation from ideal gas behavior, 22.414 liters per mole. Now we did this calculation in the ASA video, but I will repeat the calculation here. Okay, so here is my experimental value for the molar volume at STP. Okay, percent deviation equals the experimental value minus the accepted value. And our accepted value here is 22.414. That's a number you should memorize. Divide by the accepted value. Multiply by 100. My experimental value is 21, because right now I only have one trial. If I had two trials, I would use the average, but because I have one trial, I will use the trial that I have. So 21.575 liters per mole minus 22.414 liters per mole. That's my accepted value. Divide by my accepted, 22.414 liters per mole. Multiply by 100. Okay, do the math. We find that I have a negative deviation of 0.839 liters per mole, and I have a negative deviation because my experimental value is lower than the accepted. Divide by 22.414 liters per mole multiplied by 100. This will give me a percentage of negative 3.74%. Okay, and again, I have a negative percentage because my experimental molar volume at STP is lower than the accepted.